We're going to pick up and conclude our discussion of the kinetic molecular theory with a couple of related ideas taken from the two equations that we learn about the kinetic molecular model, which is the root mean square equation, URMS equals to square root of 3RT over m, and the kinetic energy equation, which is that the kinetic energy of one mole particle, the average kinetic energy, is 3/2 RT. And the one conclusion that we can get is we can model the way particles move as a collection in a sample of gas. And so this plot here is what we call the Maxwell distribution. It's written right here because that shape of the curve was derived by Maxwell. And this complex equation is not something that you will need to derive or know how to use in this class. However, it's useful to see what he's written here is basically the fraction of the particles with a certain speed can be expressed as some combination of molar mass combined with speed and temperature. And so the idea here being that the shape of this curve pretty much affected by the molar mass temperature of the particles. And so what this is telling you is that this plot is number of particles or the fraction of particles on the y-axis, and then on the x-axis is just the speed of these particles. And you can see that the particles range from really slow speed on the left side to really high speed on the right side. And then there's a distribution curve, right? It looks different than a bell curve. It's not evenly split in the middle as an average. And that's because gases don't behave like that. Specifically, we have sort of three different speeds that we can look at. The first one is the one that's right at the peak, and that's the speed that the most number of particles have. That's just called the most probable speed. So if I have randomly throw a coin and try to figure out what is the speed of this collection of particles, where I'm going to guess that most probable speed. Okay, it's also called the modal speed, U sub m. And then we have the average speed here being just taking all the particles and then averaging it out, dividing it by the total number of particles. And that's UAV right here. And then we have the root mean square velocity, URMS. And that one is the one that actually represents the kinetic energy of that collection of particles. So the URMS, of course, could be calculated using that equation we talked about before, square root of 3RT over m. Now, what's the effect of changing temperature when we have distribution like this? Well, you might imagine that if I were to increase temperature, because temperature correlates to speed, right? How do I know that? Because if I look at this equation right here, the URMS equation, temperature is on the numerator, which means that it should be proportional to the URMS. If I were to increase temperature, then the speed would also increase. So then what I would expect is that at higher temperature, this entire distribution is going to shift to the right. And that's exactly what you observe if you do an experiment. So if you start with oxygen at 273 Kelvin, if you move that sample to 1000 Kelvin, you see a shift in the number of particles from closer to the slower speed to now closer to the higher speed. Not only is the distribution shifted to the right, but you also see a reduction in the height because now the particles have a larger range of speed that it can have. So because it has a larger range of speed, there's going to be different number of particles for each of those speeds. So the overall peak of that plot is going to drop down. So what's the effect of molar masses? Well, if we look at the RMS equation, we notice that the molar mass, or m, is inversely proportional to speed. And that is kind of easy to understand. What that implies is that a smaller particle is going to move faster than a larger particle. So if your molar mass is large, the speed is going to be small. If your molar mass is small, the speed is going to be large. And that's exactly what we see here as well. If we look at oxygen again at 273, the speed is right here, the modal speed. If we replace that sample at 273 with hydrogen instead, which is a much smaller particle, it's going to move as a much faster average speed. So the modal speed is now right here instead. Now, what happens if you change oxygen to xenon, for example, which is something that's much heavier? Well, then you expect a left shift to the slower speed. The other point I want to make about the discussion we just had about the distribution of speed is this idea of the mean free path and collision frequency, which is very much important in predicting reaction speed later on, as you'll learn it in the second semester of general chemistry. So if we think about like a nitrogen molecule, for example, who's moving around right now in your room because it's the main component of air, as it's moving, it's continuing continuously changing speed because it's going to move at a specific speed and then it's going to hit another particle and it's going to change to another speed. It might go from 2,500 miles per hour in 1 second and then another second completely just standing still because it just hits another particle that causes it to pause. So comparing that movement to the size of the particle, we can calculate something called the mean free path, which is just how far can a nitrogen molecule travel before it hits something else. And if we make our calculation at a given pressure and temperature condition, we find that the mean free path for nitrogen is this distance, which is very short, but remember the molecule itself is really tiny. So that's actually a pretty large distance compared to the size of the molecule. And if you calculate that, it ends up being about 180 times the size of the particle before you run into another thing, right? So let's say you're like a 5.5 foot tall, okay? So if you multiply that by 180, right? So you would have to travel 1,000 feet in any direction before you see another human being. That's kind of the idea of this mean free path. So this is specifically with respect to nitrogen. Now, if you take the most probable speed of nitrogen and then you divide it by the mean free path, okay, what you get is then the number of collision that you're going to get every second that is experienced by the nitrogen molecule. And so if you take that speed, right, you can see here divided by that mean free path, the units cancel out. What you end up getting is collisions per second. So that tells you that in 1 second, there's a lot of collisions that are occurring between nitrogen and other particles. In fact, it's, about 7 billion collisions per second. And this number turns out to be really important for reaction rates or reaction speed, which is just how fast a reaction takes place. If I mix two reactants together, how quickly will I see product? That depends on whether those reactants are going to collide with each other and how often they collide. If they collide with each other, there's a chance that that collision might convert the reactants to products. We're going to discuss that in much more detail in Chem 12, but the collision must occur. If there's no collision, for sure there's no product. The collision for nitrogen is actually quite a bit. So you can see that a lot of reactions with these small particles occur really, really quickly. Now, as you get bigger and bigger, the speed gets slower and slower. Then there's going to be fewer collisions that are occurring per second, and therefore the reaction is going to slow down significantly.
I want to highlight this idea that we tend to use computer simulation to learn about particular microscopic system. What I want to do in this video is to have you go through a particular simulation that's based on the kinetic molecular theory. See that the simulation allows us to explain the relationships that are observed in the empirical laws, okay, Boyle's law and so on. This is really a fairly common practice these days because we have computer technology. You can program a particular mathematical equation or several mathematical equations into a computer program, and afterwards you can run these simulations to create different types of events, and that helps us understand what's going on microscopically, and that allows you to make further tests to test your hypotheses. Okay, so the particular simulation I want you to try to understand is available from this website from Oklahoma State. You can go there and play with it yourself using your own computer. I'll go through in the video and then run through a couple of the setups for the experiment of the simulation so you can actually see how it's done. The goal here is to use the simulation to explain how we get the empirical gas laws. Why is pressure and volume inversely related and so on. So we want to relate what's going on microscopically in the simulation to the macroscopic laws that we already know. The goal is really to answer the following 5 questions. Why is pressure times volume equals a constant? Why is it that when pressure goes up, volume has to go down when temperature and number of moles are constant? And all of these questions there you have to answer as well. Okay, so here's the simulation. It's fairly simple. It's basically simulating a collection of gas particles. So you can see that all of these are green particles, and they're modeled or they're simulated using that kinetic molecular theory model, which is that these are hard spheres. They have elastic collisions with each other and with the wall. And then we have a plunger that allows you to kind of change the volume up and down. And then the gases are just moving around randomly. And there's all these parameters here. Okay, so for example, if I leave the marker here on the pressure, right now we are seeing helium at 1 mole. Pressure is at 1 atmosphere. Volume is 22.4 liters. And temperature is 275 right now. I can see what's going on with a particular parameter, if I leave that mark over there. Pressure right now is marked with this. I can move it here to volume, but right now let's say I mark pressure. So if I were to change volume, the pressure would change correspondingly. Everything else will be fixed. So in other words, the only thing that's changing is the pressure and the volume. So let's try that. One of the first questions is Boyle's law. Boyle's law is P times V equals a constant. So what I want to do now is I want to change the volume of this particular simulation. So I'm going to move the volume down here. So you can see that as I click down here, you see that plunger is coming down, right? Now, what I want you to look at is here that the pressure number goes up, right, as my volume goes down. Okay, so I keep going down in volume. You can see the pressure keeps going up. Okay, the volume obviously comes down here. And why is pressure going up? What is it about the simulation that tells you that pressure is now going up? Okay, and again, you have to understand what pressure is, right, in this simulation. What is the parameter that corresponds to pressure? That again is the first question. I want to ask the second question now, which is a pressure-temperature relationship. So now you see that I'm gonna stay at pressure, but now what I want to do is I want to change temperature, and all the other factors I want to remain constant. So let's see what happens there. I'm going to lower my temperature. So you can see as my temperature comes down, my pressure also comes down, right? The number goes down, and everything else remains the same. You can see that the volume remains the same. Nothing's changing. Why is the pressure coming down? Okay, what is going on? What's happening with these particles that the pressure is now coming down? The third question I want to ask now is a volume-temperature relationship. That's Charles's law. Remember that V over T is equal to constant. So I'm going to move this down to volume. So in other words, I want volume to change as I'm changing temperature. Okay, here I'm going to lower the temperature, and you see that as I'm lowering temperature, what's going on with the volume value? You can see that the volume value here is also coming down, right? And you see the plunger slowly comes down. Okay, so the question is, why does volume have to come down to balance that temperature decrease? Okay, think about what's going on here. Why does the volume have to come down? The last law I want to talk about here, you can also explain using this simulation, is Dalton's law. So if you remember, Dalton's law is it's pretty interesting. Dalton's law says that the total pressure in a gas is equal to the partial pressure of one gas plus the partial pressure of the second gas, and so on. Okay, I can prove that to you here. Okay, you see here that pressure right now it's 1 atmosphere, right? And I have 1 mole of helium right now. Okay, so if I were to increase the number of moles of helium to 2, you see that now the pressure is 2 atmosphere, 2.02, and there's more helium here, right? Because I let in some more helium. Okay, so let's reset that. So you remember that the total pressure was 2 for 2 moles of helium. Reset that. Instead of adding 2 moles helium, I'm going to add 1 mole helium and then 1 mole neon. Now neon is a bigger gas. Okay, we know that because the molar mass of neon is about 20, molar mass of helium is about 4. Okay, so I'm going to add the neon in. Neon are these bigger blue circles. I'm going to add exactly 1 mole of neon to this thing. So now you see both neon and helium are present. Okay, you see the total pressure is 2.02, which is exactly the same as when we have 2 moles of helium. Okay, you don't believe me, you can play back that video when I added 2 moles of helium instead of 1 mole of helium and 1 mole of neon. Okay, you have the same exact number. What that does is just demonstrates Dalton's law. Dalton's law says that the pressure, total pressure, is equal to the partial pressure of gas 1, partial pressure of gas 2, and the partial pressure depends on the number of moles. The question is why? Think about it. You have something that's a lot bigger. This neon gas particles here, they're a lot bigger. And generally speaking, if you think about a situation where you have something that's a lot bigger, has a bigger mass, right? They also have a bigger force, right? So if you think about a collision between a motorcycle to a wall versus a big truck versus to a wall, that truck is going to create more damage because the truck comes in with a bigger force. That's not the case with gases. We see that whether you're adding 1 additional mole of helium or you're adding 1 additional mole of neon, you get exactly the same effect, which is the same total pressure. So the question is why? That should be pretty apparent from this simulation that is going on right now. Again, when I have 2 moles total, 1 mole helium, 1 mole neon, I get 2.02. What explains that? Why is it that adding something that's bigger doesn't make a difference in the amount of total pressure that the bigger particles contribute? Okay, it's the address for the simulation at Oklahoma State, and you just need to have Java installed in your browser in order to run